I'm not sure if you can hear me.
We can hear you.
Hello, can anyone hear me?
Yes, I can hear you.
Oh, okay, okay. So, good afternoon, everyone. Did you guys hear what I said previously?
Yes, about recursion, yeah. We heard about that. Well.
Okay, awesome, awesome. Thank you. So, I think he's okay. Speaker is here now. Yeah.
Yeah, thanks, Shay, for that introduction. Sorry, I was trying to just set up some things on my end. So, welcome everybody. Today we are going to be, am I audible enough?
Yes, you are.
Okay, perfect. Just wanted to make sure. So, today we are going to be discussing recursion, dynamic backtracking, and dynamic programming. So I noticed we're a bit few today. I was thinking, should we wait a bit for more folks to join, or should we just go ahead? Shay? Shay, organizer, are you there? Oh, he's not. Okay. So I guess we just proceed then. So today we are going to be talking about recursion, backtracking, and dynamic programming. Okay, perfect. They can always catch up. That's good. Today is going to be a bit different from what we've been used to. I'm going to be doing the lecture is not going to be too long because honestly, these concepts are not very difficult to understand. What is more important is being able to use them to solve problems. So in that vein, without wasting our time, I'm going to just get started. So we're going to be talking about a couple of things today. We're going to be talking about, we're going to be doing a recap. I remember that this is our last data structures. This is our last data structures and algorithms class. Next week is going to be more of soft skills, and final week is going to be a wrap up. So do a recap of what we've learned, just to help us get a good refresh. Then we'll talk about recursion. What is recursion? Why do we use recursion? Why is it important? Then we'll talk about backtracking. Backtracking is kind of similar to recursion, in that whenever you do recursion, you are implicitly backtracking. But again, recursion is very diverse and can be used to solve different kinds of problems. And there are so many patterns of recursion. So once you have a good grasp of recursion, then backtracking becomes very straightforward. Then we'll move to dynamic programming. Dynamic programming is one of the most fair topics. And the reason for that is most people, when learning dynamic programming, they don't use the right approach to learn it. And most people that teach dynamic programming teach it from an expert's point of view. But I'm going to be showing us a way to approach dynamic programming problems. And it's mainly going to be building your intuition because dynamic programming is very wide. It's a very broad topic. But I just want to build intuition and give some examples so that we can know how to solve this kind of problems. Then we'll spend majority of our time today problem solving. I've handpicked a couple of problems, not very much, but my goal with the problem solving session is to make sure that we know how to approach problems. So we are going to be doing is I'm going to be approaching the problem from using the different strategies we've learned in the course. And some of them might be optimal, some of them might not be optimal, but it's just to help us to have that intuition. Then for the exercises, I didn't have time to populate it yet. I would send that out in the slides later, because I was kind of rushing to prepare this. Then I'll share some resources. So without further ado, let's before we go on, so some housekeeping. Please, again, surveys are going to go out at the end of the session. Please endeavor to fill the surveys. It helps me, it helps it helps the organizers, it helps us as well. I mean, any kind of feedback is fine. And the other thing I also want to also point out is I keep saying this every session. I keep saying this every session, but I like to reiterate it each time. When I'm going through the course, when I'm going through the lecture, if you have a question, it's better to ask it immediately rather than grouping the questions to the end. So ask it immediately and I'll try to answer it. And if it's something that will take too long, then we can move it to the end of the session. All right, so let's get started. I know this has been a long ride. Kudos to you guys for staying long this far. Okay, you know me already, so let's move on. So before I get started, do we have any questions on what we've learned in the course so far? Just general questions. On anything, on any topic. Doesn't have to be related to today's topic. Okay. So I like starting with the big picture because it's helpful to know what we are learning, why we are learning it, how it fits into the bigger picture. That will carry it better. So we are used to this diagram which I shared in our previous classes. Essentially, the crux of the issue is most of the data structures and algorithms we deal with in this course are stored in RAM. And the patterns we'll be learning today, which is recursion, backtracking, and dynamic programming, are algorithms you can use on data structures that are stored in RAM. So recursion can be used across any type of data structure. Almost, in fact, all the data structures are recursive. Backtracking is a variant of recursion, and dynamic programming is also a variant of recursion. So, going back to what we discussed earlier in the course, we talked about some data structures. Remember, arrays are fundamental data structures which store items contiguously in memory. Then linked lists are the other type of basic data structures, and they store them non-contiguously. You can think of them as kind of the atomic units of data structures. You can't get more fundamental than this when you're talking about data structures. So again, when you're learning data structure, when you're looking at data structure, there are three key things you want to know how to do. You want to know how to insert things into your data structure. You want to know how to find things or search for things. And you want to know how to remove things. So those are the three key things. If you look at any data structure, that is essentially what we are doing. Because if you look at it, we are just trying to store and retrieve data. So to store data, we insert. To retrieve data, we need to remove. And to find data, we need to search for it. So again, I just put some highlights of what we've done in terms of like the big notations of arrays and linked lists. We can all go through this. So I'm gonna be talking about the algorithms we looked at. We started with searching, right? And the key thing for searching is, the key thing to remember is we need it to find items when we are retrieving data. And there are two options to search. The first one is just to search the entire collection. So you have a list, you have a dictionary, you just search everything, right? You just go from start to finish and see if you find what you're looking for. Now that's kind of the brute force, sometimes naive approach. And it's not very optimal because if you have to search for something each time you're looking for it, that takes considerable amount of time. So in terms of like searching the entire collections, we have linear search, which is like just searching an array or a linked list. And then when you have non-sequential structures, meaning tree structures and graph structures, they have their own searching mechanisms too. Depth first search, breadth first search, we've talked about those. And then for graph traversals, also we have breadth first and depth first search. So the second option is to intelligently eliminate. Now, this is only possible if the items are sorted in some form. So we looked at binary search, where you eliminate half of your remaining options each time. Ternary search is a variation of binary search, where you eliminate 2/3 of the options. Then binary search trees, again, they are stored in sorted form. Now, there are a lot of balanced binary search trees. Typically, we look at binary search trees, but there are ternary trees. Ternary trees are trees with 3 children. N-ary trees are trees with any number of children. Then we have B trees and B plus trees. So you can think of them as binary trees. You can think of them as trees that are sorted, but they have lots of children. So the reason why they exist is because the more children you have, right, the shorter the height of the tree. And in some cases, it's more efficient to have a short tree than to have a long tree. That's why all these variations exist. So we went on to sorting. And why do we sort? Because we want to make searching and retrieval fast, right? And there are a couple of ways we could do this. We could use brute force, right? Which we just check all the possible solutions. We talked about monkey sorts, where we were just trying all the possible orderings to get the solution. Then we also looked at selection sorts, and we looked at bubble sorts. There are variations of brute force. Then the key things that we also looked at were algorithmic strategies like decrease and conquer, reducing the problem to a smaller problem each time. We looked at divide and conquer, where we divide the problem into multiple smaller problems instead of one. And we looked at merge sort, quick sort, and insertion sorts. Then we look at also transforming the problem to some other form. We looked at using tree sorts, essentially storing everything in an auxiliary data structure and using that data structure to solve the problem. So these are just ways to solve problems. And we also looked at greedy last week. Last week we talked about greedy, and greedy greedy is a very funny category because it doesn't really have a pattern, right? It's essentially it selects the best possible option at present. But then the problem with that is the best possible option at present might not lead to the optimal solution eventually. So the thing about greedy algorithms is they are very efficient and they are very fast. So that's why they are important. They are very efficient and fast, but they don't have a pattern, and it's kind of difficult to be able to find a pattern to them. But usually it involves you sorting or selecting the min or the max, or the smallest or the longest, or the biggest or the smallest. It has to do with selecting the biggest or smallest of something. And usually involves heap, because if you think about it, a heap stores items in sorted. It allows you to retrieve the largest item each time or the smallest item each time. So examples of some greedy algorithms, extra, prims, and activity scheduling. I just included this for completeness. Yeah. So we are going to the main discussion of the day. Before we move forward, do we have any questions? Please go for it.
Yeah, good evening, everyone. Thank you for the class. Yeah, I would really like to ask if there are recordings to previous classes, and is it possible to get them? Hello, can you hear me?
Yes. So all the classes have been recorded. The organizers share the recordings with folks each time after the class. So I will encourage you to reach out to the organizers, and I think you provide your email or something, and then they can forward all the recordings to you.
Oh, okay, no problem. Thank you.
Yeah, yeah. Okay, so recursion. Now, recursion is a very interesting topic, and it's one of my favorite topics because it's recursion like graphs. It's difficult it looks difficult to understand, but once you understand it, it becomes easy to solve lots of problems. Now, the thing with recursion can be thought of as like a method to solve problems. It's just a method to solve problems. And the key thing with recursion is it breaks down problems into sub-problems. We saw last week, there were two ways we could break down problems. We could either break it into one smaller sub-problem, which was decrease and conquer. Sorry, last 2 weeks. Or multiple smaller sub-problems, which is divide and conquer. Now, the idea behind this is if you break down the problem into smaller problems of the same type, right, you can solve those smaller problems, right, and use those smaller problem solutions to get your own solution. And that is really the idea behind recursion. You break down the problems until you find an atomic problem you can easily solve, like one small problem you can easily solve. Then once you have that problem that you can easily solve, you can now combine the results to all the other problems that were the parents of this problem you're trying to solve. What do I mean? So you have a problem you want to solve that is too much, right? If you break it down, you can break down further down until you get to the smallest unit. Then all those subproblems cannot be aggregated back to solve the main problem. And that is the key idea behind recursion. So you can do this using, so the thing with recursion is that recursion forces you to do things this way, but you can use the same approach to do things without using recursion. But the thing with recursion is it forces you to make sure you break the problems down into subproblems. So why is recursion hard? Why is it difficult? The problem with recursion is it's a different way of thinking about problems that we are used to in real world. So if you think about loops, right? Loops are easy to understand. You can just do something over and over again. It's intuitive. You look at conditionals. You make choices. You make choices every day. So you understand, okay, if this, then that. That's easy to intuitive. It's easy to intuit. Functions, you group items together for easy management. But when it comes to recursion, what's the analogy that we do in our everyday life? Not really, right? So this is the reason why recursion is hard. It's a different way of thinking that most folks are not used to. And it does take some time to really, really understand it. So again, there are two ways we can break down a problem. We can break down into a smaller subproblem. And the way I try to explain this is, let me share my Jamboard. Yes. So imagine people are standing on a line, right? And we want to count the number of people on this line from the front. Let's say we want to count from the front. Now, how can we do this? Now, one way we could do is the person at the front, right? Where's my pen? Okay. So the person at the front knows that he's one person. He or she doesn't know the amount of people at the back of the queue. But he can ask the next person, how many people are behind you? Right? The second person doesn't know how many people are behind her. Right? Then what happens? She can ask the next person, how many people are behind you? They can't see the end of the queue. She doesn't know how many people are behind her. Right? And she asks the next person, how many people are behind you? He doesn't know either. But he knows that there's one person behind him. So he asks that person, how many people are behind you? Now, this person knows that he's the last person on the queue. There's nobody behind him. So number of people that are behind him is 0. So if he adds himself to that, he can return back to this second person and say, you know what? There is one person, behind me. There's one person behind you, which is me. That person can now take the results. So notice that when we got here, right, you could visualize this as you asking a question here, right, getting back nothing, which is 0. Then you take a 0, adding yourself to it to get 1, plus 1 here to get 1. Now, this person knows that there's one person behind. She can now say, you know what? There's one person behind me. I am one person. So I'll take the person behind me. I'll add myself, right? Now, I'll tell the person behind me that there are 2 people. Now, you can view each of these arrows as recursive calls going down the chain. And this continues on and on and on till we get to 3, till we get to 4, and finally we get to 5. Now, notice some things here. Each person doesn't know how many people are in front of them or behind them. They delegated that work to the next person. The next person solve the problem, and return the answer back to them. And this is a key thing to note in recursion. When you are trying to understand recursion, you need to look at it from the work done at one node, at one level. If you understand the work done at one level, you can use that to generalize for the entire work that will be done in the recursion process. And this is an important point to note in recursion, especially. Most people, when trying to learn recursion, they try to look at the big picture, they try to understand the whole thing. But trying to do that is going to make it difficult to understand. So just look at it from the point of view of, okay, from my own perspective, or from this perspective here, how can we solve this problem? How can I solve this problem? And then how can I break down the problem into a sub-problem and then combine the sub-problems to form my solution? Once you have that, then you've understood the main concept of recursion. Again, like I said, the concepts are not too difficult to understand. What's difficult to understand is using them to solve problems. So let's go back. Are we good with this smaller sub-problem analogy? Do we have any questions?
Yeah.
Okay. Go for it.
Yeah, good.
Okay. So now we talked about multiple sub-problems, right? And the analogy I like to use is, I need money. I don't have, let's say I'm looking for 1,000 naira and I don't have 1,000 naira. But I know 10 people that can give me 100 naira. Now, 100 naira is easier to get than 1,000 naira. So if I tell those 10 people to give me 100 naira, and those 10 people each know 10 people that could give them 10 naira, right? That makes it easy. You could break it down to say further that, okay, each of those 10 people knows 10 people that could give them 1 naira, and getting 1 naira is the easiest thing you can get. Like, you can go on the streets and get 1 naira easily. So you can see that that's a simple problem to solve. But when you begin to combine those simple problems together, you are able to solve the general problem. And that is the idea behind breaking it down to multiple sub-problems. Yes, red and black tree. Yes, it's like a pyramid scheme. Yep, that's essentially what a pyramid scheme is. A pyramid scheme is MMM, MLM. That's what they are. People at the top get money. So the further you are at the top, the higher you are, the more money you get. Essentially, that's you can. And that's a very perfect example. Thank you. So let me go to my Jamboard. No, sorry. So for this one, I just showed here each node only has 10 children. So each node has 10 children. I just showed 3 for the sake of time and space. So this is what it essentially looks like. And you notice that if you look at this one, if you look at this recursive structure, right, you could look at it as this node calling that node like this. You could look at it like this, as kind of a linear pattern. And this is a key thing to understand, that when you reduce the problem into one smaller sub-problem, right, it becomes a linear recursive structure. But when you break it down into more than one sub-problem, into multiple sub-problems, then it results in a tree recursive structure. And honestly, these are the only two types of recursive structures you can have. You can either have it as a linear structure or you have it as a tree structure. Now, the tree structures could get complicated in that they may not have the same number of children. Maybe some trees have 2 children, some trees have 3 children, some trees have 4 children. But the idea I'm trying to pass across is, if you are able to visualize recursion like in a tree form, then it makes things very easy. Now you can think of each of these nodes in the tree as a function call in the recursive tree. Now, typically, how recursion typically happens is it goes down one path at a time. So it goes down one path, right? Like this, like this. This is usually how it goes. This is how the recursive structure goes. If you follow, you see what I'm doing like this. Actually, hold on. Let me use the laser. So this is better. So it usually goes like this. If you trace the recursive calls, it goes like that. Like that. Back, like this, like this, like this, like this, like this, and like this, like this, like this. Exactly, like a product traversal, yes. Now, I would say not really, yes, it looks like a product traversal, but if you look at all the traversals, that is essentially how you go. What makes it pre-order is when you do your processing. All right. So if you look at it, Recursion traverses the tree in that particular fashion. And depending on when you do the work, right, you could have pre-order, you could have in-order, you could have post-order. So one easy way to understand, anyway, I'll talk about those later. But the key point I want to draw up here is that dividing a problem into multiple subproblems results in a tree structure. And okay, Godson, go for it. You have a question? Okay, I'll assume that was a mistake. So where was I? Good. So at any point in time, all right, the stack is only at any point in time, the recursive stack only contains items that are as deep as the height of the tree. The height of the tree is the, let me use this. So the height of the tree, come in here, yeah. So the height of the tree here, this is the deepest you can go in the recursive stack. Yeah. That's the deepest you can ever go in the recursive stack. It can't be longer than the longest part in the tree. Now, I correct that. That's essentially that's the longest part in the tree, basically, from the root to a leaf node. So this is kind of the common pattern for most recursive problems. It results in a tree structure, and if you understand the tree structure, then it makes it easier to analyze. Okay, let's move forward. Do we have any questions before I continue? Okay, so what is a recursive function? A recursive function must have three things. It must have a base case to stop the recursion. Because the recursion has to stop at some point, right? So the base case is what stops the recursion. If not, the recursion will keep going forever. Then it must have a recursive call in its function definition. That means the function must call itself. And the state must converge towards the base case, meaning that you must reduce the problem each time you're solving, either by dividing it into multiple subproblems or by reducing it into a smaller subproblem. Okay, so what happens when you don't break down the problem? So I have a recursive function here to count down, All right. But you notice here that within the function itself, I'm calling counts down again, and we are not changing the input. So what happens in this case? Essentially, what happens is, okay, I'll visualize the execution here. So what happens here is the first function gets called. That calls the second one. And it keeps going. You see that this recursion is never going to end. And all these frames are created on the stack. They are all created on the stack. So it keeps going till your stack gets full. And that's essentially what is called a stack overflow. This is a stack overflow when your stack is filled up. And what makes your stack get filled up is one of two things. Usually, it's either you have too many functions due to recursion. That's usually what causes it. You have too many function calls due to recursion. You have too many function calls stacked on top of each other. And this is why reducing the problem is important. Now, what happens? We've seen that reducing the problem does not work. Not reducing the problem doesn't work. We just overflow the stack. Now, what happens if we don't have a base case? Because I mean, we are reducing the problem, right? So if you keep reducing the problem, then what happens? What happens then is you start running, and yes, we are reducing the problem each time from 5 to 4 to 3 to 2 to 1, which is fine, reducing the problem. But the problem is we keep reducing it forever. So we fall into the same problem that we had before because we keep reducing it forever till we overflow the stack. So this is the reason why we usually say that we need a base case and we need to reduce the problem. Now, this is now a proper recursive function. You can see it has a base case. Now, sometimes the base case might not be explicit because in this case, the base case is obvious. Sometimes the base case might not really be explicit. Like I could have written this in a different way. Let me go to the visualization first. Okay, perfect. So what happens here? We call the first function countdown 5. Sorry for the ads that are disturbing. I don't think there's a way to stop this. So we call this countdown 5, all right, to 4, to 3, to 2. Now at 1, because we fit a base case now where it's n is 0, then we return. Now at this point, this is when the return starts happening. Now, because this is a linear recursive structure, we are going to return all the way back to the top. If it was a tree recursive structure, we will return and follow another path. Following that path I drew earlier on, this type of path here. So essentially what will happen is the stack will have how will I put it now? So this will be our stack here. Let me say this is our stack here. You know what? I'll talk about this later. Let's focus on this. So what happens here? Now we'll begin to return. And the functions now begin to return to their parents. And when they return to their parents, the parents, it's just like the parent function paused. And it continues from where the execution stopped. Now, because it's a linear recursive structure and it's just one thing we are doing, it's just returning back. But again, in this case, let me see. So in this case, we wrote this like this. It's obvious that this is our base case. Sometimes it's not obvious. So I could have rewritten this as this. Let me comment this out. And say if n is greater than 0. Yeah. I could have written this as this as well. Now in this case, there's a base case, but the base case is implicitly defined. It's not explicit. Like this. So this is one pattern I also wanted to take note of, that the base case might not really be explicit. Sometimes it's there. You might have to just look at the code deeply and go through it to understand. And if you visualize it, we get exactly the same results as we did last time. When we get to 0, we start going back. Okay. So I think I have another recursion visualization here. Now this is another one, another visualization, but it's still essentially the same thing. Right. So this one shows you the entire structure at once. Here. It shows you the entire structure. you can see it's a linear way, in a linear fashion. Okay, let's move on. Okay, so any questions on recursion itself, the recursive function and its structure, before we move on to doing work and returning values within the recursive function? Okay.
Not really, sir.
Do you have a question? Please, if you are not, if you don't have a question, please can you mute your mic? Okay. So please, if just endeavor to keep our mics on mute unless you have a question, so that we can make the experience better for everybody. Okay, so let's move forward. Now that we have a recursive structure, we have a couple of things we could do. Now, we could do work at different places in the recursion. We could do work before recursion, or we could do work after recursion, or we could do work in between recursion if we have multiple recursive calls. Now, what essentially happens when we do work before recursion? So in this case, it's the same countdown, but we are printing the value. So what do we do here? Essentially, what happens is that we print. So now we are calling countdown of 5. This is the first function call. What happens is we do the work, we print the value, and then we recursively call the next. We print the value and recursively call the next. On, and on. Now, notice one thing. The recursive call, right, is the last line in the recursive function. Now, when this is the case, there's something called tail optimization, meaning that it doesn't keep the parents in the stack. Tail recursion, yes, correct, tail recursion. It doesn't keep the parents in the stack. That's an optimization. Not very important, but you may come across it, so I just said to mention. So we keep going on. You see that we are doing the work before the recursion, and when we are returning, we are not doing anything. And this is essentially the order of the output. Now, what happens when we do work after recursion? After recursion, what happens here? You notice on the right, the output changes immediately. But why is that? Let's take a look at the visualization. So what happens here is when we make our function calls, because when you make a recursive call, that recursive call is done immediately. All right? It doesn't waste time. The recursive call is done immediately. So now we have not hit our base case yet. We get to a recursive call. What happens? This function is just like this function pauses, and then it calls that function. Now, in this case, because you still have work to do after the recursion, you can't do tail optimization, because you need to keep the parent in the stack, because you need to do some work after recursion. Now, we called countdown 4 now, which is the child. Now, at countdown 4, we've not hit the base case. It calls countdown 3. Now, when the recursive call is hit, it calls it immediately. It doesn't wait, but it calls it immediately. Now, we continue for countdown 3. Notice that we've not done any work yet. And we've reached the base case now. And now we've reached the base case. We are the base case, and now we return. Now, when we return back to the other function, where do we return to? We return to where that function paused, right? Which is other line. And then that now says you can print n. And then we have 1. So you can see that the order of the work now is done in reverse. The same thing, when you return back to the previous function, it continues from where that function stopped when you made the recursive call. Print2 returns, does the same thing, on and on and on. Still, we get to the final one and we're done. So you can see that where we do the recursion is important for the answers we get, even though we are kind of doing the same thing. Here, it was listed in this order. Here, it was listed in the reverse order. Now, because it's linear recursion, these are the only 2 options we have, right? We can only either do the work before or after. But you can imagine that if you have multiple recursive calls, let's say you have 2 recursive calls, you could do work before the first recursive call, you could do work between the first and the second recursive call, or you could do work after the third recursive call. Now, there's nothing that says you have to do the same work, the same pattern of work in each recursive call. And if you look at all the possible combinations you can have, right? This is what makes recursion complex. Essentially, this is why recursion is hard, because there are so many ways you can do things. You can do work before, you can do work between, you can do work after. You can do work before in sum, you can do work after in sum. You can do work every time, before, between, and after. You can only do it before, you can only do it between. So there are so many combinations. And this is why recursion is difficult. This is the major problem why recursion is difficult. The number of combinations you can have for how you can do your recursive work. Okay, so I think we get here. So do we understand the recursion itself and the order of when we do work in the recursive call, in the recursive function? Do we have any questions before I move forward? Okay, Isioma, do you have a specific question?
Yeah, so
Okay.
I get the overall idea, but where it gets a bit confusing is where the work is done. I'd like to know like how to visualize the difference between when the work is done before the recursive call and when it's done after the recursive call. I didn't quite get that.
Okay, so the reason why it's difficult to visualize is because whether the work is done before the recursive call or after the recursive call, the tree structure visualization is the same. Like the structure of the tree is the same, right? What makes it different are your outputs and your return values. That is what makes you know, okay, if you are doing work before or you are doing work after. Like I said here, so I think a good way to do this would be, okay, let me go back to this Jamboard. So this is a tree recursive structure. Right? Doing work before, between, or after is not really obvious from this tree here, right? It's more about the output or the result you get and what they're returning from each node. But I think using an example might make it a bit more clearer. Let me see. So using an example might make it a bit more clearer. But the main idea is, if you do work before the recursion, and if you do work after recursion, it changes the output. That is the main idea. And that's the main idea which you got already. But knowing whether you are doing work before, between, or after from the visualization, it's not very easy to determine because the structure is the same. You have to look at the return values and the output you are getting or what you are passing out. But we'll take examples to see how that works. So going back to our tree structures where we had pre-order, in-order, and post-order. If you recall, in pre-order, we're doing the work before any recursive call. In-order, we're doing the work between the left call and the right call, between the two calls, because we just had two. In post-order, we're doing the work after both of them. So that is why you had those three patterns. Now, I would say, like, try and understand the main idea. Then as you begin to solve problems, you begin to understand how to know when it's before or after. Does that answer your question?
Yes.
Okay. Let me see. Okay. So returning values during recursion. Now we've talked about the recursive call itself. Now, but during recursion, you can also return values as well. So sometimes you return values, sometimes you don't. Sometimes you return values, sometimes you just add to a result. But returning values, let's see how it works. So we are trying to compute factorial. Now the factorial of a number is multiplying the number by one less than itself till you get to 1. So the factorial of 5, for instance, is 5 times 4 times 3 times 2 times 1. An easy way to understand factorial is by understanding that if you have the factorial of 1 less than the current number, you can multiply that result by the current number to get your answer. And this is the key idea behind the factorial. Now, if you keep doing that, when do we hit our base case? When we get to 0. I put less than or equal to 0 here just to be safe, but you can just make it equal to 0 as well. It's still the same effect. Now, what happens with the return values when we start visualizing? There's nothing unusual here. We don't hit our base case. Now, notice something. When we get to this line, we are meant to return. But because the code is executed left to right, it has to complete this factorial of n minus 1 before returning this whole function. So it gets stuck here and then goes to complete factorial of n minus 1, which is factorial of 4. The factorial of 4 continues in the same fashion and completes the factorial of 3. Factorial of 2, factorial of 1, factorial of 0. Now we hit our base case and we return. Now, when we return back to the parent function on that line, and the return value of the function call in the parent gets assigned to our return value, to the current value. So what do I mean? The factorial of 0 is 1. So when we return back here, our return value here is 1, which means that this side here is 1, right? And then we can multiply that by 1 and return back to 2. Multiply that by 2, return back to 3, like that, like that, like that. So you get your answer. So this is returning calls during recursion. And the key to understand is that when you are returning during recursion, it returns back to where it stopped and assigns the value, the return value, to that call within the function. Are we clear on this? Is it too much? Am I going too fast? Okay.
No, sir.
Okay, please ask your question.
Please, what's the factorial of 0? Are you going to go into negative like -1, or what's the factorial of 0?
Mathematically, the factorial of 0 is, I think, is 1. The factorial of 0 is 1. I don't know the reason. I don't know the reason for that. It's weird. It's a very weird thing, but mathematicians decided that the factorial of 0 is 1.
Okay.
Yeah, I guess it's kind of confusing, right? But for some reason, they just decided that the factorial of 0 is 1. Yes, There's some long articles on how they came about that we don't really need to go into. But you can look that up if you're interested. So let me see. Yeah, so this is what happens when you return values during recursion. Now, the reason why I'm using these simple examples to illustrate it is that if you understand it with these simple examples, it's easier when you start looking at more complicated examples that have recursive calls or anywhere or anyhow. But remember that the most complicated recursion structure you can get is a tree structure. You cannot get more complicated than a tree structure. Like, there is no way you can get a more complicated recursive code than a tree structure. There is no way. So the tree could be very big. It could have 1 million children. Some could have 2 children, some could have 3 children, some could have 1 child, some could have no child. But that's how complicated you can get recursion. It doesn't get more complicated than that. Okay, so let's see the second visualization. Okay, so for this one, I use this. Okay, good. This one shows you how the calls go and how things get returned. So you have the calls going down the stack, and then it starts returning. Perfect. So 2 major variations of recursion. Linear recursion, which you've dealt with. And usually it's all the examples you've considered in this class. So you can think of each recursive call as a node in the tree. And you can visualize it like a linked list. So let's see what this looks like. So 1 second. Factorial numbers. Yeah. So you can see that it's a tree. Now I'm going to show us different recursive structures and see how the trees look like. Some of them are complicated, but don't mind. Don't bother about what it's doing. Just understand, see how the different trees look like. Binary search. Why is it like this? Because you are reducing the problem to one smaller subproblem, which is half of the original problem. Modulo power. We don't need to get into it, but we can see the structure. Greatest common divisor to the same thing. Max range sum, linear. Catalan numbers, linear. You don't need to understand what they do. I just want to point out the tree structure. Fibonacci numbers. Now we start to see the tree structure. We'll talk about Fibonacci when we ask our next example, but you can see that this tree is a very funny tree. Is it a balanced tree? It's not really balanced. How do we analyze it? It's funny, right? This one has 2 children. This one has no child. It's not the same level. It's a very funny tree. But we'll get to that as we go on. This is another tree. I think this is a combination. This is another type of recursive tree. This here now. This is what I'm talking about. Can see this tree is funny. This one has 3 children here. This one has 2 children. You see what I'm saying? This one has 3. This one has 2. This one has so. This is how complicated. This is how the recursive structure generally happens. It forms a tree somehow. Then see this one. It's a very, very funny structure. A funny structure. So these are other problems that you don't need to think about. But now look at merge sort. Look at merge sort, right? Merge sort is this merge sort recursive structure. If we record our sorting class. Quick sort 2 is the same thing. Actually, this is a bad quick sort. This is a quick sort that is not balanced, where you don't choose the pivots correctly. Now, this is the randomized quick sort. This is the balanced quick sort. You see that tree is now more balanced. I think we don't need to bother about all this again. Yeah, we don't need to bother about all this. But I just wanted to show you this so that you can understand that it just the most complicated recursion structure just generate a tree. And if you can understand the tree, then it makes your understanding of recursion very easy. Okay, let's move on to tree recursion. So tree recursion, what happens in tree recursion? You make multiple recursive calls. You can make 1, you can make 2, you can make 3, you can make 4, you can make 10, you can make 5 sometimes, 6 sometimes. It's arbitrary. Now we saw this in divide and conquer algorithms that we looked at, which was merge sort and quick sort. Now, typically, you also see this when you are doing recursion on trees and graphs. You see this when you're doing recursion on trees and graphs. So when you do a depth first search on a graph with recursion or on a tree, essentially that's what you're doing. With a tree, you're making two recursive calls because you just have with a binary tree, you're making two recursive calls. But in a graph, you could have any number of children. So again, like I said earlier, the recursive process can be visualized as trees. And each recursive call can be thought of as a node. So why is this important? Because it helps model complex solutions more effectively. And you can usually visualize it like a tree. Okay. So before we go into an example of tree recursion, do we have any questions? Okay. So Fibonacci. Fibonacci is a classic example of recursion where the fib of one number is the sum of the fib of the last two numbers. This essentially is the definition of a Fibonacci series. So it's actually a series and n-1 and n-2. This is it. Now, the key thing to understand here is that it makes two recursive calls. And one is the reason why the tree is somehow because one reduces the problem by one reduces the problem by two. So the one that reduces the problem by one results in a longer tree. The one that reduces the problem by two results in a shorter tree. Now, I'm going to go by the visualization of how this works. I think this is not a good place to start. I think we should start with this one. Okay. So this is essentially the visualization of. So I want to do fib of 5. Sorry, I need to make sure I. Okay. Where am I? Okay, perfect. So we start at the beginning. All right. And we start going. We start from fib of 5. At fib of 5, we call fib of 4, which is the left side of the recursive structure. That's on. Let me try and see if I can make this bigger. So essentially, we didn't hit the base case, and then we are at this core here. Now, what happens going forward is funny. Where is my cursor? Okay. So essentially, fib of 4, it calls that immediately. Fib of 5 causes. Cause fib of 3. Fib of 2. Now, when we get to 1, what happens? We hit our base case. And then we return back. But when we return back, remember, we've done the left side of the recursion. Now we need to do the right side of the recursion, the other side of the recursion. And essentially what happens now is we now call fib of 0, which is the right side. So you notice what I said on how the tree is going. It goes from the left down and keeps going down. It goes down, back up, back down, up, down, like that till it passes everything. Okay, so we continue here. Fib of 0 is 1. Fib of 2 returns back to fib of 3, which now calls fib of 1, the other side of the recursion. The same thing happens when we are done with fib of 3. We go to fib of 4 and go to the right side to call fib of 2. But notice something. We know the answer to fib of 2, right? Because we did fib of 2 here. Now we have to go recompute fib of 2 again here. Because we already know that if this is the fib of 2, then we know that this part of the tree is going to be equal to this part of the tree. We don't need to go do all this work again. So, not doing this repeated work is what is called dynamic programming. That is what dynamic programming is, essentially. Not doing repeated work. So let's continue and see what happens here. How do we know we have seen fib of 2? Because in our tree here, so in our tree here, we've already saw fib of 2. In our tree, if you followed how we went through the tree. Now, this fib of 2 here is computed because we are currently trying to compute fib of 4. And in fib of 4, we need to compute fib of n minus 2, which is fib of 2. But when we computed fib of 3, right? When we computed fib of 3, which we've computed already, because we are currently computing fib of 4, we computed fib of n minus 1, which is fib of 2. So we computed this one, we're computing fib of 3. Now we are computing it again, we are computing fib of 4. It's double work. Does that answer your question? You can keep track of sum of values for every node. Yes, correct. So you can keep track of what you've computed and just use them and just provide your answer immediately, which is caching or memoization. Like a cache, exactly. And this is what is called dynamic. This is what is dynamic programming. Now, I'll explain why dynamic programming looks complicated later on. But keep this at the back of your mind that this, if you can generate a recursive structure well and find repeated work you are doing and cache, then you can solve dynamic programming problems. So, and notice as we're going down the tree, we are returning back up, right? That returning back up is what backtracking is. So you can see that recursion, backtracking, and dynamic programming, they are all recursion. There's nothing specific that says, okay, this is backtracking. But you do backtracking every time. With dynamic programming, it's a bit different, but it's all part of recursion. So the key thing to understand is how recursion works, how to generate a recursive tree, and how to understand the recursive tree. I think I missed the comments in the chat. So the main computation begins after hitting the base case. In this case, yes, because you are returning values. But if you are doing work before you made the recursive call, then your computation will have started before you even hit the base case. But in that case, you can't return values. You can only update something or print something, do something that has a side effect, or update a global variable. You can't return values in that case. If you are returning values from recursion, you have to do the work after the base case returns, yes. Okay. So let's continue our tree structure here that we are looking at. So we call fib of 2. Now fib of 2, we call fib of 1 and fib of 0, which is duplicate work. Now notice again, this fib of 1 here we are computing. We are repeating it here, we are repeating it here. Fib of 0, we are repeating it here, we are repeating it here. But because it doesn't have a subtree, it's not really a big deal, it's constant. I just wanted to point it out. Okay, let's move on. So now, we know our fib of 2 is 1. We knew that already. It was just a wasted work. We now go back. Where are we? Here. 1 second. Okay, so we go back now. And we know we can compute fib of, oh no, sorry. Let me take this back. we are here. Okay, we are here. Yes, we are here. Sorry for the confusion. Okay, so now get fib of 0. We can now add fib of 1 and fib of 0 to get fib of 2. And we can now compute the right-hand side to compute fib of 3. Now, look at it again. Fib of 3 is repeated work here. This here is repeated. It's repeated work essentially. So I'm just going to waste time here doing all this. And there we go. So we get back to fib of 5. So this is how tree recursion works. Now, how does it look like here? Now we've seen how it looked like from the tree perspective. But when you look at it from the stack, what do we see? So let's start. So we compute fib of 5. Compute fib of 5, we not hit the base case. We come here, we compute fib of n-1, compute fib of 3, we get to fib of 2, we get to fib of 1. Sorry, when we get to fib of 2, our base case, these are our base case. In this case, this is how I wrote the code. Don't worry about that later. But when we return back, right, we continue from where we stopped and return back. Now, notice something as we go on the tree, as we return back, the tree, it becomes bigger sometimes. You see what I mean? Because it's just one part of the tree you're following. You're not following, you can't follow the whole tree. And the stack is only as big as the height of the tree, the longest part in the tree. And that is how it's different. You should be looking at it that way. Are we clear? Do we have questions? Okay. So now we've done tree recursion. So the reason why recursion is important is because a lot of data structures are recursive. And recursive data structures that appear in their definition. So if you look at a linked list, if you look at the definition of a linked list, it has a node, it has a next node and a value. Now, the next node itself is another linked list. Look at the tree. The left side of the tree is a subtree. The right side is a subtree. If you look at the graph, all the children of the graph are subgraphs in their own minds. If you remove the current node from the graph, what do I mean? This is recursive data structure. The first node is a linked list. The next one is a linked list, like that. So if you keep removing one node, you get a smaller linked list, which is like solving a smaller recursive problem. Same thing with trees. The left tree is a subtree, the right tree is a subtree. So if you do recursion to the left and right subtrees, you are solving a smaller problem. You are solving a smaller tree. With graphs, the same thing. You remove one node from the graph, you are solving a smaller graph. So one thing I wanted to also call out is recursion versus iteration. Now, so you can see that if you look at what recursion is essentially doing, recursion is doing something over and over again, all right, till it gets to a base case. So you can always use iteration instead of recursion. And one key thing to know is that all recursive code can be converted to iterative code and vice versa. For linear recursion, it's straightforward. You can use a for loop for a while. But for tree recursion, it's sometimes not straightforward. You might need to use a stack. But that stack is a user-created stack that is on the heap. It's not the system stack. We talked about this when we looked at stack and queues, if you remember. But the reason why recursion is important is that it makes solving problems easier. And in the real world applications, it helps you solve problems. It helps you know that, okay, you can solve problems in a certain way. But iteration is usually favored over recursion because of the cost, because of the call stack, because of the stack size. So when you do recursion, you're using the system stack, but the system stack is small. When you use iteration with a user stack, you are using a stack that is on the heap, which is theoretically infinite memory. I mean, as big as the amount of memory you have. Sorry. So that's one thing to consider about recursion and iteration. So we're done with recursion here. Like I said, the concepts are not difficult to understand. It's applying them that is the problem. So we're done with recursion now. And do we have any questions before we go into backtracking? Are we still happy? Are we tired? Do we want to take a break?
No, not at all.
Okay. So for backtracking, it's the definition that you typically find is, they say it's a technique for trying out all possible solutions and choosing all of them or the best ones. But what backtracking really means is, as you are going down the recursive tree, you either any advantages of recursion over iteration. Okay, so advantages of recursion over iteration is, to be honest, the only advantage is that it makes solving problems easier. In terms of efficiency, it is not more efficient than iteration. No, it is worse because of the space complexity. Because each function call you make takes space. You don't have to do everything within one function, right? When you make a function call, you have to allocate stack space. And each of those functions have their own stack frame, which takes space and memory. So theoretically, they tell you that the time complexity is O of n or O of this, but in reality, the implications are much worse than that. So no, recursion is not better than iteration for solving real world problems. The only good thing is that solutions are easier to see with recursion. That is the major advantage. And sometimes the iterative code can be very cumbersome. It's very cumbersome. Like you could be having too many for loops, or you could be having too many stacks. Like so for every recursive code, you can convert it to iteration. No matter how complicated it is, you can create the stack yourself manually. Because if you look at what a recursive code is doing essentially, let me go back to my visualization. It's just, let me see. So with this now, let me use this now. If you have truly recursive, you're just going like this. All right, down, like this, on and on. So you can simulate this using a stack. You can simulate this whole thing using a stack. Like you create a stack, you add to it, then you create and add different smaller stacks to it. There are nuances about how you do that, which is not, I don't want to go into those. But no, iteration is better than recursion. And the only advantage recursion has is that it's more efficient. It's easier to solve problems. It's easier to spot the solution of a problem. Let me put it that. Let me see. Next question. Can I get access to the previous lectures? Yes. So I think reach out to the organizers. They can get you access to the previous lectures. Okay. So before we move on, let me see. So essentially, what backtracking here is that it's one of two things. Is either you don't explore the whole recursive tree because some solutions are not necessary, or you explore everything, right, and choose a solution. But again, whenever you do recursion normally, you backtrack when you are returning. You see the thing. So the definition is more like, okay, you are trying possible solution and choosing them all, but it's not really very different. It's just that you are stopping the recursion early if you don't have a solution. That is what backtracking is. So you are doing recursion, but you see that at this point, there's no point continuing with this subtree, because there's no solution here. Then you can just go back, return quickly. So if a path is invalid, it backtracks and goes down a different path. Essentially, that is what it's saying. So if I simulate what I'm saying here on this line here. So let's say we're going down this path, right? And we got here and we discovered that we don't have any other solution. We could just backtrack immediately and come here. There's no solution here, we can just backtrack immediately. So that will save you competing unnecessarily these ones, all these sites here. So let me give an example. So let's say our solution was here. Let's say this was our solution. It doesn't matter what you're solving. We are going to have a recursive tree, and our solution is somewhere here. Now, the solution could be at this node, or it could be along this path. But the key thing to notice is that when you are doing recursion like that, let's say you were going to explore, so let's say you were not backtracking. You have to explore the whole tree. Explore, go around before you come to your solution here. But if you were backtracking and you came here and discovered that, okay, I can't find the answer here, you could just go back immediately. I can't find the answer here, go back immediately, come here. I can't find the answer here and here, and just go here and get your answer. So that is the fundamental idea behind backtracking. You are trying out something, and if it doesn't work, you go back. So the best analogy for this is, let's say you are in a maze, and you are in the middle of the maze. There's an exit to the maze, but the maze, not all paths lead to an exit, and you're looking for the exit. So what do? And you don't have a map. So you just keep walking. You keep walking. Okay, so you have a question. Okay, I assume that's a mistake. So you keep walking along a path. Now, if you are walking along a path and it's just one path, you're good. You just keep walking. But when you see a crossroad, you have to make a choice between either going to one side. Quick question: are caches necessary for backtracking since we need information from other parts to decide which is optimal? No, caches are not necessary for backtracking. So the thing is, the path is not a valid solution from the path itself. You don't need. So again, let me rephrase. It depends on what you're solving. All right. If you are looking for the best path in the solution, that means you have to evaluate all the paths. In that case, you need information from other paths. But if you are not looking for the best path, or you are looking for a certain solution, you don't need information from all the paths. You can just know from the current path itself whether it's a solution or not. Are caches necessary for backtracking? No, they are not necessary for backtracking. Caches are necessary for dynamic programming, not backtracking. Dynamic programming and backtracking are different. Dynamic programming is, I've seen this solution before, I don't want to solve it again. Backtracking is, this solution cannot give me an answer, I don't want to solve it at all. Okay, so going back to our maze analogy. So you keep walking, right? When you get to an intersection, you have to make a choice, whether you go one side or the other side. But as you're making a choice, you want to remember where you were. So you probably just leave a breadcrumb as you're going. Now, if you follow the left path and you see that you hit a wall, you know that there's no answer there, you have to go back, right? And try the other side. Now, when you look at all the possible combinations of trying all the possible paths, you are going to explore the whole maze, which will generate a tree of each path you took. And one of those paths is your answer. But you don't know which one unless you evaluate almost everything till you get your answer, right? So that is, you have to evaluate till you get your answer. Once you get your answer, you're done. That is one variation. But if you're looking for the shortest path, then you have to evaluate everything and determine which one is the shortest. That's a different variation. But the fundamental idea is, you are going down with recursive path, and you are going down with path, and you're like, this part does not give me an answer. I'm not completing the answer at all, and you return back. Okay, so do we understand backtracking? So the general template is this. This is the general template for backtracking. you have a path, and you can choose from certain options, right? If you get to the end condition as your base case, if it's the end condition, then you're done. Just return. You add the result, the path to your results. Now, the path could be a value. You could be adding things along the path. You could be multiplying along the path. You could be grouping the path to a list. Doesn't matter. But you're doing something with the path you are following. Now, if you are not at your base case, then at this part, since I have to make a selection, I make a selection. Like I go to one side. If that works, I'm good. If it doesn't, I have to deselect it and try the other selection. Now, notice that when you try and make a selection at this line here, at this backtrack line, if that gives you an answer, if it hits a base case and you return back here, right, it continues from here. So depending on how you want to do it, you could explore all the parts. You could stop when you see your answer. It's arbitrary. What's important is you are making a decision whether you want to continue completing that part or not. So I think, yeah, that's it about backtracking. Do you have any questions? Okay. Dynamic programming, the beast of them all. So dynamic programming is one of the most fair topics because it's kind of made to look a lot more complicated than it really is. But what it really is that you are doing recursion without repetition. So essentially, you so a question says backtracking seems like a version of greedy programming. So again, so backtracking deals with exploring paths. You're exploring multiple paths, and you're backtracking to explore another path. Greedy says, I'm only following one path, and I'm only following the best path I think is my answer now. Let me give an analogy from what we've done before. So let me see. How can I do this now? Okay, let's see this. This is not a good example. Okay, let me try and use this one. So we know that our solution is here, right? If we're doing a greedy solution, right? Greedy will have said, okay, when we are here, we need to make a choice. Greedy doesn't go through multiple paths. Greedy goes through one path. Greedy will be like, okay, I have to choose one from here. Now, in this case, they are equal, but let's say you choose this one. You can choose this one and choose this one, and this is not the answer. And then the greedy algorithm is not correct. So greedy is just going through one path and picking, using some heuristic, either the smallest or the minimum to pick whichever path is going through to find the answer. But backtracking is, I will try this path. If it doesn't work, I'll try another path. But while I'm trying the path, if I come across a path that is not leading me to a likely solution, I don't continue trying it. Okay. So yeah. So let's continue here. Okay. So what it really is you cache results to prevent unnecessary recomputations. That is the key thing about dynamic programming. Now there are two variations to it. There's the top-down, which is recursion with memoization. Now there's the bottom-up, which is iterative. Now, the bottom-up is difficult to come up with on your own. It's very difficult to come up with on your own if you are not really used to dynamic programming. So what I would recommend is understand recursion very well and try to memorize your recursion. And the truth is, for interviews, recursion with memorization is sufficient. It's more than enough. If you can do recursion with memorization, you're good. And yeah, that's really it about dynamic programming. Now, going bottom up is nice. If you can solve the bottom up is good, it's nice, but it's not easy to come up with the solution on its own. It is not easy. It's not intuitive at all. It comes with practice. So usually what most people do is because they've solved lots of dynamic programming problems, they know the solutions to these problems and they memorize it. Then they come up with the bottom-up solution. But then when you begin to probe how they came up across that, they can't really tell you how. And that's a good way to know if somebody, and that's a good way to know if someone is memorizing an answer. Because when you begin to ask questions on the solution, they can't give you how they got there. So it's better to understand recursion and use memorization and understand it intuitively than trying to do bottom-up immediately. Bottom-up is difficult to come up with. And so there's a question. For greedy algo, you might not get the correct answer. Correct. You might not get the correct answer. Yes. Yes. That is the major disadvantage of greedy algorithms. That's why you need to be sure that your greedy algorithm will give you a correct answer. Sometimes you're not getting, so you might not get it. So sometimes it might not be correct versus incorrect. It might just be some answers are better than the others. But to get the best answer is too much work. But we can use an answer that is not perfect, but that still meets some certain conditions. So that's where greedy comes into play. A classic example of this is the traveling salesman problem. The traveling salesman problem says, if you have a salesman that has to go through different cities, right, and come back to his starting spot, what is the most efficient way this salesman can go? So let's say you have distance between different cities, and the salesman has to deliver a mail to all those cities and come back to where he's starting from. What is the most efficient way he or she can go? As simple as that problem sounds, people have been studying this thing for years and they've not found a solution to it. There is no, so the only solution, right, is to enumerate all the possible paths the salesman can pass and pick the best. But that's not efficient because the time complexity is too bad. Right? So, but there are greedy algorithms that will give you a good solution, not the best. Sometimes you are lucky you get the best. They'll give you a good solution that is not the best. But it's fast and it's easy, and you can use it. You can use it for a very large input size. So, are you saying iteration with recursion is bottom-up dynamic? Are you saying iteration within recursion is bottom-up dynamic? No. So, iteration and recursion are separate. Iteration is bottom-up dynamic. Recursion and memorization is top-down dynamic. I hope that answers your question. If it doesn't, let me know. Okay, so let's proceed. So why do you even bother with dynamic programming? Why is it important? The key thing is that it reduces the time complexity from exponential or factorial to quadratic or even linear. And why does it do this? Because you are not repeating the work you are doing. You are not solving the work you solved before. You are using capped values. That's why it improves the efficiency. So it makes otherwise unsolvable problems solvable within an acceptable time frame. So back to our classic example, Fibonacci. I mean, I explained this earlier where essentially, no, not this, sorry. Yeah, I'm using a different one here. So I think we could. So without memorization, what happens here? You can see it's a bit fast, but you can see the recursive calls. Yes. So yes, I would give you an instance of bottom up. So when you are doing problem solving, even with Fibonacci, we'll start from top down without memorization. Top down, so we start from top down, which is we first start with basic recursion to solve the problem. Then recursion with memorization. Then from there we'll now go bottom up. Just to give example. So you can see here that this tree here, the fundamental problem here is we've solved the fib of 1. We've solved the fib of 0. Now we're solving the fib of 1 again. But it's not a problem because we just return immediately. But now we are solving the fib of 2 again, which we've solved here. See the problem. This is duplicate work. And it might not seem like a lot, but when you aggregate the duplicate work, it becomes a big deal. So you see this now. Now we get to fib of 5. We are going to repeat 3 again. But we've done 3 here. And you can see the 3 for 3 is pretty large. So you can imagine if you are computing a very large fib, like this becomes very inefficient pretty fast. 2, 1, back up, 2, 1, like that. And oh, sorry, I missed something here. And to even make matters worse, right? When we're computing 3, come back here. When we're computing 3 here, we are computing 2, which we've computed here, and we've computed here. So we are doing multiple repeated works that gets bigger. So that is why dynamic programming is important. So a quick solution is just to say, you know what, I've seen 2 before, I don't need to recompute it again. That's a very quick solution. And that is what the memorization part does. Now, what happens here? You can see that because we've saved the answers, we are saving ourselves from that tree, from the exponential, from the big tree. Essentially, we now have something like almost a linear recursive structure. Because when we come here, we compute 1. But now, when we want to compute 2 here, we don't go compute again because we've computed it before. I don't want to compute 3. We don't do all this repeated work because we computed it here before. And that is what memorization does. So we improved our tree from this right to this. Okay, so we've seen our Fibonacci visualization now. What is time and space complexity? So how do we analyze recursive functions? This is important. So the general rule of a recursive function is, if you think about what you're doing, you take the number of nodes in the tree and multiply it by the amount of work you've done per node. That's the general formula. And to get the number of nodes in a recursive tree, for a full recursive tree, like a tree that has equal children, it's usually the number of branches raised to the power depth. What do I mean? Let me come back to this and change this to n-1 minimization. And I want this to be fib of 4. Okay, let's see now what happens. Now, this is a balanced tree. You know that all the nodes have the same number of children. Now, if you want to calculate the number of nodes in this tree, what is it? The short formula is 2 to the power of the height of the tree. 2 to the power 0 is 1. This is 1 node. 2 to the power 1 is 2. Right? 2 to the power 2 is 4. So essentially, you have 7 powers of 2. In this case, 2 because it's 2 children. If it was 3 children, it would be 7 powers of 3. And if you take the summation of all the nodes, right, you notice that all the nodes at the bottom all the nodes at the top, right, are less than all the nodes at the bottom here. So you have 8 nodes at the bottom, you have 7 nodes at the top. So the general formula is 2 to the power of the height of the tree plus 1 minus 1. But those details are not really important. Just know that it's exponential 2 to the power of number of branches by the depth. In terms of big O, we don't care about all those plus 1 minus 1. So that's how to get the number of nodes in the recursive tree. Now, for the work done per node, you do your regular analysis within the function and see what the function is doing. Now, for the space complexity, this is essentially the depth of the tree, because the tree generally has a height. So this is how deep the tree is, right? Multiplied by the space you consume at each node of the tree. Yes, multiplied by the average space, the space you consume or the average space you consume at each node. So those are the general rules, but sometimes the general rules do not work. They cannot be used. Why is that? Because you might have a variable number of branches. And in cases like this, looking at the total work done is more helpful. Like, okay, look at it that, what's the total work I'm doing here? So you can look at it at total work done per line, like we did when we were analyzing merge sorts and quick sorts. But you can look at the total work done in total, which we will do as in some of the examples I'll show. So the same goes for space complexity. You can look at the total amount of space stored. But the truth is, without doing mathematical analysis, it's more of an art than the science. So let's analyze the time and space complexity of the recursive of Fibonacci without recursion, without memoization. Number of nodes in the recursive tree is 2 to the n. This is simplified because the tree is not really balanced, but it doesn't really matter for our purposes. Number of nodes in the recursive tree is 2 to the n because we care about the order of magnitude. I think it's kind of like 1.6 to the n, really, but it's not really important. That analysis is too complicated. So the work done per node is constant. So this is time complexity of the Fibonacci function with recursion without memoization. You can see that this is exponential. This is exponential, and this is not acceptable. It's too bad. The time complexity is too bad. The space complexity is the depth of the tree and the space complexity at each node. Depth of the tree is O of n. Because n, we start from fib of 5 and we go to 4, 3, 2, 1 down the tree. So the depth of the tree is O of n. The space consumed at each node is O of 1, which is just O of n. Now, this is time and space complexity of recursion without memoization. When we memorize, now this is what I just did in memoization here. You use a cache. Essentially, it's the same function, but you have a cache to store the result of your computation. And you first check in the cache if you have your previous answer and return it immediately. Now, what's the time complexity of this? Number of nodes in the recursive tree. How many nodes do we have in this recursive tree? It's funny, right? It's kind of like you have a line, and then for each line you have another child. So you can look at it like 2 times n. So which is 2n. The work done per node is constant. And O of 2n is O of n. So you can see that we reduce from exponential to linear. That's why dynamic programming is very important. It's very useful. Now, the space complexity is the depth of the tree and space consumed at each node, right? But in this case now, because at each node we have a cache, so we have to consider the cache as part of the space consumed. Now, the truth is, knowing what the cache is storing at each function call is not easy. But I do know that by the time the function is done, the cache is going to be full. That means the biggest the cache can get is as big as the number of function calls I have to make, which is n. So the cache can only get as big as n, the order of magnitude. That's why I said looking at total work done can be helpful. So in that case now, the cache size is O of n, and the depth of the tree itself is O of n. When you add those two, it's still O of n. Now, using iteration only. This is essentially the same thing I did here. Essentially the same thing here. But what you are doing here is you're starting from the bottom, right? You populating. So previously you start from the top and go down. But now we are starting from 0. We are populating 0 and 1. Then we are going from 2 to n plus 1, because it's not inclusive in Python. It's exclusive in Python. Then we complete fib of n minus 1 plus fib of n minus 2, which we already have in the cache because we are going bottom up. And then we store that in our cache to use for the next computations. So when we're done, we return our answer. So this is essentially what bottom up is. But coming up with this straightforward. Now in Fibonacci, you might say, okay, maybe it's easier to come up with this. But in a lot of problems, coming up with this on its own is not easy. It is not easy at all. So let's see what we have here. Okay. So this is just, I don't think there's anything special to show here, because this is just a normal function. It doesn't have recursion, it's just normal things we've been doing normally. So the cache I'm using here is a hash table, it's a hash map. You could use an array, you could use a hash map, it doesn't really matter as far as you get the cache. So we run the code here, populate our cache with 0 and 1. So this is like saying, okay, I know fib of 0 and I know fib of 1. Now I want to compute fib of 2. I know fib of 2 is fib of 0 plus fib of 1, which I already have because it's already in the cache. So I fetch them from the cache, compute fib of 2, and continue. Now I need to compute fib of 3. Right? Fib of 3 is fib of 2 plus fib of 1. Fib of 2 is in the cache, fib of 1 is in the cache. So I just pull them out and I add them together. And I continue till I get to 5. And I return fib of 5 from the cache. That is essentially bottom up. Now, what's time and space complexity here? This should be a little bit straightforward because we just have one for loop, right? So on this cache line, what are we doing? It's just variable assignments. This is constant. Okay, we have a for loop. We are going to n. Okay, we are going from 2 to n, which is kind of n minus 2, but doesn't matter, it's still n. Then here we are just taking values from the cache, which is constant, taking values from a cache, which is constant, assigning them back to the cache, which is constant. Array access is constant. And when you are using a hash map, essentially you are using an array under the hood. So it's still constant. O of n twice. Yes, I think you are. I'm not sure which answer you're responding to, but let's continue. So you return the cache of n. So I think it's O of n. I mean, it doesn't matter if you say it's O of n twice because it's the O of n, but I'm curious as to how you arrived at O of n twice. Bottom up, yes. Yeah, but I'm not sure of how it's O of n twice because we are just doing one for loop and we're not doing 2 for loops. So I think it's just O of n, but you are still correct. For both, let me see. Oh, I see what you mean. Got you. Sorry. Yeah. So O of n for time complexity and O of n for space complexity. Because from space complexity, if you look at it, you are storing your space complexity here is limited by the cache. And the cache can get as big as n. So in this case, it's helpful to look at the total work you're doing to analyze the problem. Okay, so yeah, because of cache storage. So this is bottom up. Notice that time complexity of bottom up and recursion with memorization is still the same. But there's an additional advantage. So now, if you look at this clearly, you discover that what you need is just the previous value and the second previous value. When I'm computing fib of 5, I don't need to know what fib of 1 is. I just need fib of 4 and fib of 3. So at each time, I just need previous 2 values. So that tells me that I might not need to use this whole cache. I just need to store the last three values, like a moving cache that stores the most recent values. That's essentially what I need. And that's what this does. It uses two values to store fib of 0 and fib of 1. Then as we go on from 2 to n plus 1, we store the fib of 2 in temporary. So this is fib of 2 here at this point. This fib of 2. Now, we now shift. So essentially, we are shifting. We are assigning A to B and B to fib of 2. So essentially, what you are doing is you have fib of 0, you have fib of 1. That's what you're storing. You are taking a fib of 0 and fib of 1, and you are storing fib of 1 and fib of 2 in those variables. So if you do that, right, what happens then is your time complexity is still the same, but your space complexity now becomes constant. And this is the main advantage of bottom-up here, because the space complexity is smaller. And this is the reason why iteration is preferred over recursion, generally. So this is an example of, so look at where we started from. Let's go back to where we started from. We started from just recursion, naked recursion, to recursion with memoization, to bottom-up, and then to the optimized bottom-up. If you can get this optimized bottom-up, generally, at the first go, that's very impressive. But generally, if you even get to this one here, this is very impressive on its own. This, for the sake of interviews, is sufficient. That's the reality. So yeah, this is like how dynamic programming patterns usually go. And so usually the problem is when you're looking at dynamic programming solutions, they usually start from here or here. They start from bottom up. That's what most people that do the solutions do. They don't really go down from top down and explain the intuition behind how they got here. Okay, so that's it about, that's it about dynamic programming. So it means the optimized bottom-up loop calculates the add up and finally return last. So it means the optimized bottom-up loop calculates the add up and finally return the last sum value. Yes, correct. Correct. Yeah, that's what it does. It does what this does, except that, so if you can visualize it as this one storing all the values, you can visualize the cache as deleting every other thing except the last two values. That is what it is. So I just use variables to represent it here, but you could have written it in a way such that you use the cache and use the cache with a fixed size or a moving queue, whichever one. Yeah. Okay, so that's it for our lecture. So if you look at it really, recursion dynamic programming it's not really, can we do without temvar? Yes, you can actually. In Python, you don't need temvar. I just did this because some of us are not really Python. We're not what they call it now. So if you could just do this, so you could do A comma B is equal to, yep, exactly. A, B comma A plus B, yep. Yeah. Python allows these cheats here. But normally for most other languages, it's kind of like you have to use a temp variable to assign it. So that's why I just wrote it like this. So now we're going to problem solve it. So I'm going to go through problems and I'm going to try and see how I can break down the intuition behind the problems, most importantly. So again, I went through this template last 2 weeks. So this is kind of like what I use when I'm trying to solve problems. This is kind of like a rough idea. So you first try to look at it and say, okay, if I explain this to a 2-year-old or a 3-year-old, how would you solve it? Because sometimes, because you know too much, so you start looking for complicated solutions. But if you just look at it from a very basic way, like what is the basic solution first? Sometimes the solution is just right there standing in front of you, and it's very simple. It's simple solutions like that. Now, you now see if you can chip away at the problem. Like, okay, this problem is too large. Can I reduce this problem? Or can I build a solution incrementally? You can see if you can reduce the problem into smaller problems and combine the results. That doesn't work, then you just brainstorm through your data structures and see which one you can apply. Then estimate the time and space complexity of each and decide on the one you want to go with. So this is just a general framework. You don't have to follow it top down. Some questions don't follow this pattern. It's just a general framework. But specifically for recursion, try to focus on the work done at one stage of the recursive process. Don't think about the whole recursive process. Think about one stage of the recursive process. So think about what your base case would be and think about what one stage of the recursive process does. Once you have those two, you have a recursive function. You don't need to worry about how everything works. So the key thing is don't overload yourself with the whole picture. And find the recursive solution to a problem and then try to memorize it or cache it. Going straight to bottom-up iterative solution is difficult. And it's not really feasible for most folks. In most cases. It's not because questions are not intuitive enough for you to just come up with bottom-up direct. With the Fibonacci and easier problems, maybe it's obvious. But with like more difficult problems, it's not obvious at all. Okay, so we have some problem solving here for exercises because I was rushing to make the slides. I couldn't. I saw too many. So the issue with recursion and dynamic programming is that so many exercises around. So I was trying to look for like the good ones. So I'll populate this later and share it with the slides. For resources too, the other resources I've shared previously, and I added some recursion visualizers here that you can use. Those are the only two additions with the resources here, really. So before we go into the problems, do we have any questions? Okay, so I assume we understand everything. Is that a safe assumption?
Yeah, thank you very much, sir. As for me, it's actually clear enough. So, but let's see the exercises. So I think, of course, most people have questions in that regard.
Okay, sounds good. So I just selected some problems here. Let's see this reverse string problem. Okay, so for the reverse string problem, okay, perfect. So for the reverse string problem here, we have this question here that says, write a function that reverses a string, right? The input string is given as an array of characters. You must do this by modifying the input array in place with O of 1 extra memory. So this problem looks easy, right? It's just to reverse a string. You can call it a reverse function. But I selected this problem because there are lots of ways you can solve the problem, just to go through different approaches. So that's a question. If one has a time test, do one think of using brute force first or using an efficient solution? So it depends on what type of test you are doing. If you are doing a test that is going to be marked by a computer, right? And they tell you that they are more interested in you getting the answer, just get the answer however you can. Doesn't matter. If you are doing an interview, if you are doing it and they say the efficiency is important, then what about efficiency? But for most time tests I have experienced or encountered, they don't usually require you to be efficient. They just want you to solve the problem. And then, because the tests are usually like a screening phase first, before they now do a real interview. But for a live interview, you want to show that you understand different approaches and you can pick an efficient solution. Maybe not the most efficient, but an efficient solution that is satisfactory with the interview. So this is like a 2-pointer, yes. For muscle memory, you know that, okay, you can use 2-pointer to solve this problem. But let's take a step back and see, okay, if we want to solve this problem, like, What is the easiest way to solve it? Now they say we should do it in place. So that's the problem, right? With all of one extra memory. Well, let's relax the constraint a bit. Let's say we don't have all of one extra memory. And they just say we should do it in place. Just for the purposes of learning. Then what can we do? I mean, we can create a new array, copy it to the new array, and start from the back and populate the current array, right? That's one way we could do it. Or, let's see, can we decrease the problem somehow? Can we reduce this problem? So how that would look like is, let me go to the Jamboard. Okay. So this is my string here. Hello. So the question I'll ask myself is if somehow I'm able to reverse these strings, how can I add this H to the result to give my answer? So let's say somehow, miraculously, I have this. I have this. How will H fit in here? I just add it to the end, right? So you can see a pattern. Then what is your base case when you get to one element? So you can solve the problem that way by doing it in a recursive way. I think that is what this is here. Is it recursive way? Is this recursive way? Yeah, this is recursive way. Yes, this is recursive way. Oops, sorry. So this is recursive way here. Essentially, what you are doing is you are reversing the rest of the string here. Actually, this is a different solution. Sorry, this is a different solution. My bad. That's a different solution. That is one way to do it. But if you want to do it recursively with 2 pointers, you can also do it that way, right? So you just move from the outward, swap, move inward, swap continuously. You can do it iteratively, you can do it recursively. And that is what this is here. So, but going back to the problem solving strategy I was talking about, like we divide and conquer, we can see that we can solve the problem by this pattern here. So now, if we decide that, okay, we've solved this problem here. So if we say we want to solve this problem, so let's say now we are at ELLO. H has delegated the problem to solve ELLO. If I take out E, and I'm somehow able to reverse this, right? I can just add E to this, right? And if I take OLL, and I repeat the same process, and I'm somehow able to reverse this, I can just add this to it. If I take LL, and I repeat the same process, and I have L, and I just add L to it. Now, if I take this one, this becomes my base case. You can see how reducing the problem helps you build up back to the final solution. So this is the decrease and conquer in a way, because you're reducing into one sub-problem, one smaller problem. Now, that's that. But if you think about it, that's one way to solve it. What of divide and conquer? Can we divide this and conquer this solution? Can we divide and conquer this problem? It might not look obvious, but let's see. So for divide and conquer, let me say I have HELLO here. HELLO. Let's say somehow miraculously I divide this into two. And I'm somehow able to solve this, and I'm somehow able to solve the left and the right. Can I get my results from solving the left and the right? Yes. What do I need to do? I put the right first, and I put the left. So this tells me that I can use divide and conquer to solve this. But notice I'm not looking at the whole recursive structure. I'm looking at a certain point. I'm assuming I can solve this and I can solve this. And I'm combining the answer here. That's really what I'm doing here. Now, how I solve these individual ones is just a repeat of the same process again and again and again. So this way you can use divide and conquer to solve this. Maybe not as efficient, but you can use it to solve this. And I think that is this one here. Now, so I use this to illustrate the fact that, let me see. I use this to illustrate the fact that problem solving strategies coming, you can use them to solve different problems. Like this type of problem now, it's not something you use this for normally because it's a simpler problem. But for some problems, this is maybe the only obvious solution you can come across. So you can use divide and conquer to solve it like this. Okay, so let's see. So which other ones? So decrease and conquer works, divide and conquer works. So let's see if we can transform the problem. So let's say we want to brainstorm data structures, for instance. We try and use an array. It's already an array, right? A stack and a queue doesn't really help us. I mean, we can use a stack, but it's just that we have to insert it to the stack in a certain order. So in this case, here we can make it work. If we want to use other data structures by force, we can make it work. But if we don't need it in this case because it's just less efficient. In fact, all the data structures can work with it. Reverse string, this, let me see. So if j is less than 0, return your string. Okay, so you have your I and j reversed. Okay. I'm not sure this would work. I'm not entirely sure this would work. I think your idea is correct, but I'm not sure if that implementation will work. I need to look at it more in a bit more detail. But let me go over the other problems. Then I would look at the code in detail. So that's it about that. So I illustrated this problem to show that like problem solving strategies are just arbitrary. You can solve them in any way. It's just have to look for the right one. Here we know that okay, it's straightforward at 2-pointer. But if it's only straightforward, you have to start looking for how to solve. So for backtracking, there's this problem I selected, which is generate parentheses. So what is it? It's saying giving m pairs of parentheses, write the function to generate all combinations of well-formed parentheses. What does this mean? So let's say n is 1. We can either have this or this, right? None of this is valid. So when n is 2, you can either have this, actually, so you can have, so it says the pairs, sorry, so when n is 1, you can have only n, 2, 4, yeah. So when n is 1, when n is 1, you have is 2 actually you are looking for. So you can have this, you can have this. So let's look at this. So you can have this, right? First, and you can have this. Now from this one, you can have this. So from this one, you can have this and this. Or you can have this and this. And for this, you can have this and this. Or you can have this and this. So this is, so looking at this already, I can tell that if I generate all the possible combinations of all the parentheses I can have, I can just filter for the correct ones and select my answer. Now, where does backtracking come into play? I know that this, so if let's say I know that this can never give me a correct answer. So let's say n was equal to 3. Let me make it bigger. So let's say n was equal to 3. So I start with this, right? When I'm generating my recursion. I start with either this or this. Now that is your recursive tree going down. This is one recursive tree, this is one recursive tree, which will generate other children. But if I have this, right, and I add, what can I add to this? I could add this and this, or I could have this and this. Now, this is still a valid solution, right? This is still a valid solution. This is still a valid solution. But can this ever be a valid solution? No, because if you look at it, I can either add this and this. Sorry, this and this, or this and this. No matter what I add going forward, this can never be a valid solution. So this is where you backtrack. This is an instance of where you backtrack and stop competing this. Because there's no point continuing. It's never going to give me a good solution here. But if we come here now and say, okay, we have these two. So how can we further subdivide this? We could have this, this, and this, right? Or we could have what was there before and the other one. Can this still give me a solution? Yeah. Can this still give me a solution? Yeah. Because why is that? Because the left is more than the right. Now for this one, how does this work? I could either have this, right, or this. Can this still give me a solution? Yeah. But can this give me a solution? No. So essentially, when the number of right parentheses become greater than the left parentheses, then there's no solution you can have there. So I can stop processing this. I can just stop here. I can backtrack here and not continue processing this tree inside here. You see the pattern for me. We continue here. When we get here, we can either add this, 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 and this, or we can either have this, 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 and this. Are these still valid solutions? Because we know we are going to 3 and we are going to 6 characters, because it says pairs, 6 characters. We know that this cannot be a valid solution again. So we can stop processing this. Because we only have 2 left and it's not going to be balanced. But this can still be a valid solution. Let's continue with this. So we can have this, this, and this, and this. Or this, 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 and this. Can this still be a valid solution? Yeah. We still have 2 here to make it valid. Can this still be a valid solution? Yeah. We could have this open and close to make it valid. So we'll continue processing them. This is still a valid solution, so we'll process it as well. Oops. You have this, this, and this. You can add this. Or you can have this, this, and this, and you can have this. Is this still a valid solution? Yeah. This is a valid solution? Yeah. Continue processing. You see how with the backtracking, you are pruning areas away from the tree that you don't need. And this is the fundamental idea of backtracking. Here. Now, if you continue doing it, we'll eventually get our answer. But I think this illustrates the idea. So I'm going to stop here. And let me see what we have here. I think, yeah, this is essentially the recursion with backtracking solution here. So what are we doing? Like I said, it's the same template. It's just that I'm trying to reuse the current variable here. So if the deficit is less than 0, essentially, if the right is greater than the left, then we return. We don't have any solution. This is where we backtrack. If we have an answer, then I add it to the answer and I return. Rather than that, I try to add the left, make the recursive call, remove. So this popping is like, I'm undoing what I did here. I'm undoing this, adding the right and making the recursive call. Exactly. Do you have any questions? Or is it too is it not clear enough?
Actually, thank you very much, sir.
So I didn't okay, that's fine.
Question. Yeah.
Okay, so let's move on. I think I will leave this. So for the permutations, it's kind of similar. I'll go to dynamic programming. I think this is a good one to illustrate dynamic programming. So what does it say? It says there's a robot at the end of this grid here. The robot is located here. The robot tries to move to the bottom right corner. So the robot is moving here. But the robot can only go down or right at any point in time. So given two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. So this is one path the robot can take, right? This is another path. This is another path. This is another path. This is another path. See, there are plenty, but they want you to return the number. So looking at this, like how this problem looks complicated and looks like it's a difficult problem, but how do you solve it now? Like, okay, so let's see. Let's try and break the problem down. So the question is, if I'm here as a robot, let's assume I don't know how big the thing is. If I know the number of paths it takes me if I move down, and I know the number of paths it takes me if I move right, can I get the total number of paths to get here? That's the fundamental question to ask. And then discover that
Can you
if
repeat
from
that
this
question?
robot, right
Sorry.
here,
Okay.
you know the number
Okay.
of unique paths if you go down, and you know the number of unique paths if you go right. Do you know the number of unique paths these robots can take to get to the destination? If they are, go on, please. Okay. So if you have only two paths, so if they say you are in a maze, right, and they say find the number of paths it takes you to get to the end of the maze, there are many paths, but you have only two paths in front of you right now. I know that this path takes me 5. There are 5 paths through this way, and there are 6 paths through this way. What does that tell me? It tells me that there are 11 paths in total, right, that I can go through, because I can either go to one side or the other.
Yeah.
And that's all you need to generate a recursive structure for this question. You don't need to care about the whole work. So you now ask yourself, what would be the base case at this point? Because it doesn't matter if you are here or you are here or you are here. The formula is still the same. What will be the base case if you are? So if you are here, what is the base case? I mean, it's just how many parts? It's one part, right? Which you are there. If you are here, it's just one part to get there. If you are here, it's one part to get here. So these two squares can be your base case. Or this could be your base case. So if I try to fill this out in a square form, let me try and see if this would, let me go back to the jam mode. Okay, I think you can do this like this. So open a new board here. So we have the robot and we have, let me see. Let me make a small graph, a small board here. Well, actually, I think this is better. Okay, let's make it small like this. And then let me make it, yeah, this is fine. So if you are here, how many ways can you use to get to the destination? You're already at the destination, right? So it's just one way. Or you can look at it as 0 ways, depends. If you are here right? You can only go down. You can't go right. That means it's just one way. Now, since you know the answer to these two, can you know the answer to this one? You can only go this way, right? It's just one way because it's only this way you can go. So you take how many ways you can go from here and just add one here. Now, can I calculate this now? Yes, because I can only go right. Right? So this is one way as well. Now, can I calculate this? Put this well so that it's a bit clearer. Can I calculate this one here? It is summation of going right and going down, which is 1 plus 1. So that means there are 2 ways here. So now I have this and this. Can I calculate this? Yes, 2 plus 1 is 3. So there are 3 ways to go from here to here, which is going here, and going here. Is that correct? Yes, because you can only go down, all right? So you can go here, here, here. You can go here, here, here. You can go here, here, here. Yep. So it's 3 ways. You can see how just understanding that you need to see the work from one place gives the solution to this. Let's look at the solution here. Oh. What's happening? Okay. So if you look at this, yeah. This is essentially the recursive. So this is the recursive structure here. Let me make it bigger. I will share this later when I format the notes properly. I've not included them in the notes yet. But this is essentially the base case. Here, what I'm checking for is out of bounds. If I'm out of bounds of the matrix, then if you are at the last point, there's one way at the last point. Then you add number of ways going down, add the number of ways going right, and this gives you your answer. Now, this is just a Pythonic way is Python allows you to easily cache functions. But I could have written this using the cache as well with memorization. So this cache just caches the result here. It's like a decorator. It just caches the result of that function. It's like you can look at it like calling a function within a function, essentially. Oh yeah, so that's a classic example of dynamic programming. Now, can I do bottom up for this? Yes, I can. But let me see. Did I ever do bottom up here? I don't know if I ever did bottom up though. Nah, I never did bottom up. Yeah, but you can solve it in bottom up as well. So yeah, permutation and subset are kind of similar. Let me just briefly touch through them. So with permutations, permutation is saying you want to generate all the possible orderings of the number, right? So let's try and solve this normally. So let's say I have 1, 2, 3. How can I generate the permutations? So generating permutation of 1, 2, 3 might be too much. So let's say somehow I'm able to generate the permutations of 2 and 3. Can I add 1 to this solution? That's the question. Well, it means if I want to add 1 to generating permutation of 2 and 3, right? What that means then is that it's going to be 1 can be first. It can be between 2 and 3. Or it can be after 2 and 3. You see this pattern here? That is essentially what it is. Actually, hold on. Yeah. So this is one way to do it. Or, so since I know that this is a possible permutation now here, I think there's something I'm missing. No, actually, there's something I'm missing. I take that back. No. So what is the possible permutation of 2 and 3. Sorry. It could be 2 and 3 or 3 and 2, right? Is it that 2 is first or 3 is second, right? So if we know this is the answer, how can we add 1 to these solutions here? Well, I know that if I want to add 1 to this solution, I could add 1 in the beginning of this solution. I could add 1 to the middle of this solution. Or I could add 1 after the solution. The same thing here. I could add 1 before. I could add 1 between. Or I could add 1 after. So this is assuming I was able to generate the permutation of 2 and 3. Now, how do I generate the permutation of 2 and 3? Let's assume I'm miraculously able to generate the permutation of 3. I don't know how. What does that say about 2? It means 2 can either be in front or 2 can either be at the back, which is 3. Which is so 2 can either be at the front or 2 can either be at the back. Now, how can I generate the permutation of 3? Well, the permutation of 3 is 3 is the only one. And that's how you can use recursion to solve this problem. But I want you to understand the intuition behind it before going to the code. Now, each of these, so this can be done iteratively, can also be done recursively as well. So let me see. I think I have good solutions here. I have the iterative solution here. This is the iterative solution. And this is also the recursive solution. I will share it later. Now, for subsets are kind of similar, but they are different in that when you're generating subsets do not care about the ordering. So let's say I have 1, 2, 3, and I want to generate the subsets. All the possible subsets are empty sets, 1, 2, 3. This is the answer. I'm just saying the answer to illustrate what subsets mean. The subset just means all the possible orderings of all the elements, which it can be thought of as all the possible combinations, I think. So this is 1, 2, 1, 3. Can have 2, 3. I think 1, 2, 1, 3, 2, 3. 2, 1, 2, 1 is the same thing as 2, 1, 2, 3. Then you have 1, 2, 3. Yeah, you have 1, 2, 3. So how do you generate this? Normally, this is the answer I'm expecting. But let's say I want to generate this now. What's the intuition behind this? Again, it's too much work. Let's say I'm able to generate all the possible subsets with 2 and 3. Somehow I'm able to generate all the possible subsets with 2 and 3. How can I insert 1 to this subset with 2 and 3? So now let's keep that problem and say, okay, how do we generate the problem subset of 2 and 3? So if I say I'm able to generate the subset of 2, how can I insert 2 to the answer of 3? And let's keep that problem and say, okay, we want to generate the subset of 3. Subset of 3 is just 3. So we can return 3 back. Now, if we know that the subset of 3 is 3, so actually, subset of 3 is 3, and it's 3, yes, and the empty set. Because it could also mean nothing. Or we could forget about the empty set and just include it implicitly. Actually, no, we can't. And the empty set, yeah, we need to include the empty set, meaning nothing is there. Because the empty 3 can either be in the set or not be in the set. This is a subset. The empty set is also a subset. 3 can either be in or not in. That's it. So if you come here, and this is our answer here for the subset of 3, how can we put 2 to use these answers here? How can I put 2 to use these answers here? Well, since this is one subset, we know that we can either add 2 to this subset or we don't add 2. And we can either add, You can either add to this subset, or we don't add to. Do you see? So this now tells me that these are all the possible subsets of this. Now, can I use this here, back in my answer here, to find what be the subset when I include one? Well, yes, I can. I mean, if I have this, I know that these are my possible subsets. I can either include one here, which is 3, 2, 1, or I don't include it, which is 3, 2. Right? Or I can include one here, which is 3, 1. Or I don't include it, which is just 3. Or I can include one here, which is 2, 1. Or I don't include it, which is just 2. Or I can include it here, which is 1. Or I don't include it. And this gives me the same as this. So this is kind of the intuition behind like using recursion to work through these problems. I think I have there's the iterative solution here and also the recursive solution as well. I'll share this after the class here. Okay, I think I've covered everything I wanted to cover. I know this has been I'll update the exercises later when I share this. Yeah, I think we're done. Any other questions before we call it a day? I think this is our last technical class. Yeah, this is our last like technical class. Yeah, I think next week is going to be more of just interview preparation. My colleague will be taking that, more of like interview preparation and solving questions. So yeah, I think we've reached the end of the road today. And if anybody has any questions, you can drop it in the Slack. Sometimes I forget to monitor the Slack. So please, if you ask a question and I don't answer on time, just ping me or mention me again. I would make sure I answer. But I do check it frequently. But this last week has just been a very busy week for me. That was why I wasn't monitoring the chat very well. Yeah. Okay. So yeah, I'll hand it over to the organizers now at this point.
Thank you so much. It was a great session. We really enjoyed the session and we've learned a lot from this. Thank you. So guys, please, we are going to publish the recordings on YouTube, so you guys can go back there and check if you are missing anything or you want to know more about something. So as he has mentioned, please, if you have any question, reach out to him on Slack. I'll be there to answer your question. So next week will be it is going to be more of like how to solve interview questions. It's going to be like a live coding session by Soji. So thank you so much, everyone, and have a great evening.
Thank you, everyone. Bye.